In this video, we will look at several examples of circuit analysis. So how we use what we know about the behavior of electric circuits to predict various quantities, what we might measure in an electric circuit. So we'll just look at a few examples. So just to sort of outline sort of the procedure. So in circuit analysis, we use what we know about the behavior of electric current to determine unknowns in an electric circuit. So we might ask ourselves, so what do we know about the behavior of electric circuits? Well, we know Kirchhoff's laws, and remember there are two of them, Kirchhoff's current law and Kirchhoff's voltage law. Kirchhoff's current law basically says that the current that flows into a junction must be equal to the total current that flows out. And Kirchhoff's voltage law basically says that around any complete path in a circuit, the sum of the increases in electric potential must be equal to the sum of the decreases in electric potential. So in other words, they add up to 0. Ohm's law is something else we know about the behavior of electricity in electric circuits. And we also know how to add resistors when they're in series and in parallel. So of course in series you just add the resistors together, but in parallel, remember you have to take 1 over each resistance, add them together to get 1 over the total. And we also talked a little bit about electric power, which might come in and be helpful from time to time as well. All right, well, let's look at a few simple examples. So here's the first one, just a fairly simple series circuit. It consists of 3 10-ohm resistors all in series and a 12-volt power source. And what we want to find in this first problem is the total resistance, the current through the circuit, and the voltage drop across R2. So we know for a series circuit that we just add the resistances together. That will give us the total equivalent resistance. So it's simply 10 plus 10 plus 10, which gives us 30 ohms. The current then in the circuit will be the voltage from the source divided by the total equivalent resistance. So 12 volts divided by 30, which gives us 0.4 amps. So the current everywhere in that circuit will be the same. It'll be 0.4 amps. If we then want to calculate the voltage drop across R2, so remember what happens is when current flows through a resistor, electric potential energy is lost, which results in a voltage drop. So the current is 0.4 amps, R2 is 10 ohms, and that gives us a voltage drop of 4 volts. Notice, by the way, that the voltage drop across R1 and the voltage drop across R3, those will both also be equal to 4 volts as well. And notice that 4 plus 4 plus 4 would add up to a total of 12. Okay, so this is just a fairly simple example of circuit analysis for a series circuit. Let's look at a fairly simple parallel example. So here we have two 20-ohm lamps connected in parallel to a 6-volt source. Find the total equivalent resistance, and then I1, and I2, and the voltage drop across each lamp. Again, fairly straightforward. So remember that the total equivalent resistance will be 1 over R1 plus 1 over R2. So that's 1 over 20 plus 1 over 20, which gives us a total equivalent resistance of 10 ohms. Once we have that total resistance, we can find the current, I. So it'll be the voltage from the source divided by the total resistance. So 6 volts divided by 10, which would give us 0.6. Okay. Now we have a couple of different options as to how we can proceed. So one way would be to suggest that, well, because R1 and R2 are the same, the current is going to split in half. So half the current will go through R1, half the current will go through R2. So I1 and I2 will both be 0.3 amps. So that's one way to proceed with the solution. Remember as well that around any complete path, the sum of the increases and decreases in voltage must be 0. So that means that the voltage drop across R1 is going to be 6, and the voltage drop across R2 will also be 6. All right. Now, if we had have done this part first, we could then go and calculate the currents, I1 and I2, just using V over R1. So if the voltage drop across R1 is 6 and R1 is 20 ohms, notice how that gives us 0.3 amps, which is what we assumed previously. And of course, we could do the same for I2, and of course, we get the same result as well. So in these types of questions, there will often be sort of multiple ways that you can continue through the problem to arrive at the final answer. All right, so let's just try one more, and let's try one more that's maybe a little bit different. Let's try a combination series parallel circuit. So here's a series parallel circuit. Power source 12 volts. We've got 3 resistors, R1, R2, and R3. R1 is 5 ohms, R2 and R3 are 10 ohms. And what we want to find is we want to find the total equivalent resistance. We want to find all 3 currents and all 3 voltage drops in the circuit. If you want to give this a try, pause the video, give it a try, and then come back. And of course, I will go over the answer. All right, so to come up with these solutions, so the first thing to do is to look at the resistors R2 and R3. Those 2 resistors are in parallel. So let's find their equivalent parallel resistance. So if we take 1 over 10 plus 1 over 10, we'll get the total parallel resistance, which is 5. So that means what we could do is actually take R2 and R3, and we could, if we wanted to, take them right out of the circuit and replace them with a single resistor of 5 ohms. So then that 5 ohms is then in series with R1, which is also 5 ohms. So the total resistance of the circuit in this example is 10 ohms. We can then find the current coming from the power source, so what we would call I1, and that would be the voltage from the source divided by the total equivalent resistance, so 12 volts divided by 10 ohms, which gives us 1.2 amps. Now again, we have a couple of different ways that we could proceed. One way to go is we could calculate V1 by taking I1 times R1, so 1.2 amps times 5 ohms, which gives us 6 volts. Once we have that, we could then figure out what V2 and V3 are. So using Kirchhoff's voltage law, we know around any complete path, the sum of the increases and decreases must be 0. So V1 and V2 around that path must add up to 12. So V1 and V2 must both be equal to 6. And V3 must also be 6. Now once we have those voltages, we could then find the currents, I2 and I3. So I2 would be V2 over R2, which gives 0.6 amps. And of course, we could do the same calculation for I3, and we also get 0.6 amps. Notice as well that the current again splits in half, so R2 and R3 are the same. Half the current goes through R2, half the current goes through R3. And of course, we could have started with that assumption and then used those currents to instead calculate V2 and V3. So these are just 3 fairly simple examples of what we call circuit analysis. Obviously, they can get more challenging than this, so I would encourage you to try some other examples. But these 3 examples show you the essential methods and procedures that we use for circuit analysis.